Testing, testing. 1, 2, 3. All right, we're back, everybody. Thank you very much for joining us again. Here it is, lesson 4.0 of our 2024 STEMNetX Data Science Workshop. I'm functioning on very little sleep. Let's see how this goes. Your patience will be greatly appreciated. So we've covered a lot of basic programming skills and then also some kind of core data science skills or simulation skills up to this point. What I want to do in this lesson is take a little bit of a fun diversion, a fun little jaunt down a kind of a different alley of investigation. What we're going to do in this lesson is treat textual information as data. Now, you may have heard of fields such as digital humanities or cryptography. These are very cool, like cryptography is not so new. Digital humanities as an idea is newer, relatively new as an academic discipline or an area of research. And these can in some ways rely on applying data science tools to language and how we use natural language. What we're going to do today is we're going to do that. We're going to apply some of our programming and data science skills to language data sets or word data sets, textual data sets. And the reason that I think this lesson is very important, very useful, is because we're going to treat it as an opportunity to develop some scientific questions about text and then implement code, write some computer code that is an implementation of those questions or answers those questions or investigates the things that we want to know. So let's jump right into it. Now, unlike previous lessons, I don't have to explain to you, what language is, or not that I could. The idea of language is a very complicated concept. Let's not overthink it. So you can read this section about this lesson, something completely different. Let's start with a data file that is available to you on GitHub. It's this file called words_alpha.txt. Now this file is quite interesting. It contains 370,102 English language words. Some of them, whether or not they are words, is maybe a little bit questionable. They're strings of characters that you've probably never seen together. That's totally fine. They've appeared in some text somewhere. The person who created this data set and their code is available on GitHub. You can see how they put it together. Now, there's the source right there. What we're going to do with this data set is read it in and consider the information that's in it on the individual word level and try to gain some kind of higher level statistical understanding of these words that appear in the English language. So I have a little block of code down here, and we're just going to start with this first warm-up problem. And actually, maybe let me show you what this file looks like real quick. So here it is, words alpha. Let's open it in the Jupyter browser. Here's what it looks like. It's an alphabetical ordered list of words. So A is definitely a word. I've used that word before. Is a word in the English language. It's actually a word that comes from Hawaiian. I think it refers to a type of lava or maybe a type of magma. AAA, that doesn't seem like an English word to me. So there's maybe some junk in here. I don't want that to be rude. Maybe somebody knows what the word AAA means. But you can see there's a lot of words in here if we just kind of scroll down to another chunk of the alphabet. Fabula, I believe that's a word. Fabular. Fac, I don't know about that. If you watched The Bear on Hulu or FX, maybe you know about Fac, the character. There's a lot of stuff going on in here. We're going to ignore the question of whether these are all really words, and we're just going to do some analysis of the data set as a whole. So the code that you see here, nothing shocking. We're importing NumPy. I've set up a little string, which I call alphabet, and it's just the lowercase letters of the alphabet. We're going to open the file wordsalpha.txt in read mode, and then we're going to read off the first line. We're going to do some stuff inside this while loop, and the while loop is set up in a way that we've used in the past. It's just going to continue reading lines off of the file until the lines no longer have any information in them. So let's do this. What's the first problem here? Read in the file line by line and determine how many words begin with the letter M. Okay, so lowercase m. So I guess what I want to do here is I'm going to have a couple counter variables. I'm going to initialize n words and n m words as my counter variables. I'm going to start them both at 0. And then every time I read in a word, I'm going to increment n words plus equals 1. Remember, that's a really compact Pythonic syntax for increment the value that's stored in that variable by 1. And then I just need to check if line the 0th element of that line is equal to lowercase m character, what I'm going to do is increment nm words by 1. And down here, after I close the file, I'm going to print total word count. Ooh, when I'm low on sleep, my typing suffers. And this is going to be n words. And then I'll just copy this line. M word count like this. And I'll print out m words. All right, is this going to work for us? I think this is going to work. I don't see any obvious problems that I made. So let's run this and let's see what happens. Oh goodness, that was quick. Okay, so there are 370,000 words in this file. That makes sense. I think up here I said it was 370,102. So we're getting a few more. Maybe that previous count is incorrect. It's, plus minus 3 is not a big deal. And then the number of m words we found is 20,000, 19,805. I believe that. That seems reasonable. Let's check the next question. So are there any that begin with capital M? Well, I can easily change this. I'll just change the character that I'm looking for in the 0th element of that string. Remember that kind of list syntax here for a string just means grab me the I equals 0 index character in that word. And I'll probably change this down here just so we know what we're looking at. Okay, great. So there were 0 words that began with capital M. So this is, very basic. It gives us an approximation of the fraction of words in the English language that start with the letter M. If you believe that this words alpha.txt is the end-all be-all, it's a totally comprehensive, exhaustive list of all of the words in the English language, and you believe that we wrote this code correctly, then you can trust that, roughly 20,000 of the words in the English language begin with the letter M. So this is kind of the tip of the iceberg. At this point, we're investigating the properties of these words. I have a bunch more warm-up problems down here. Let's just choose one of these, and we'll do another one kind of on the fly here. All right, so let's do warm-up 3. How many 5-letter words are there in the data set? Okay, so how would we do that? Well, we'd have to check the length of each one of those words that we read in. That shouldn't be too bad to do. What I'm going to do is I'm going to grab most of the code from above here, copy it, and then just paste it down here. Okay, there we go. Okay, so I want to count the number of 5-letter words. Here I'm going to have the total. So I'll call this next variable, I'll just call it n5 words. It's kind of a weird variable name, but it's going to do the same thing, same-ish thing. It's going to count up the number of 5-letter words. All right, here I need to be a little bit more careful. So what I'm going to do is I'm reading in a line from the file. In this situation, I have to be careful. So I want to know the length of the line that I've read in, like that. I want to check that this thing is equal to 5. And let's do the following. So I'm going to, if that's the case, I'll increment 5 words. And just to check to make sure we're counting up the right things, like this conditional is working the way we think it should, let's print out the line that we're getting. So there's 1 word per line in this file, hopefully we think so. We're going to read off that line, we'll increment the total number of words, and then we'll check whether that line is 5 characters long, if the length of the line is equal to 5. If so, we'll print the line just as a sanity check, and if so, we'll increment our counter number of 5 words. So, okay, let's change this to 5-letter word count, and I'm going to change this variable to n5 words. Any other problems? Do you see any other problems if I run this? I don't hear you telling me anything, so I'm going to go ahead and run it. Let's live dangerously. Oh, goodness. Well, that's weird. So it found 0 words that are 5 characters long or 5 letters long. Let's see, can anybody tell what I did wrong? This might be a lack of sleep issue. So here I applied the function len to line, which gives us a number that is probably an integer, the length of the line. And then I've checked to see whether it's equal to 5 What's the type of that 5? This is a string 5. That's not what I mean. I'm checking whether a number is equal to a string. That's never going to work. So I want to make that equal to 5, the integer. This should go a little bit better. Okay, so we're getting some words now. What do you notice about these words? You should be noticing that they are not 5 characters long. And the reason for that, there's another kind of telling clue here, which is that when I print out the line, I'm getting not just the word, but I'm getting like a blank line after that. I think the reason for that is that when I read the line out of the file, each one of those lines has a hidden new line character at the end of it, which basically tells the file, hey, the next word is on the next line, the next word is on the next line. I want to remove that thing. So I'm going to use the function strip, or like that. So if line is a string, line.strip returns the line with all of the hidden characters and blank spaces removed from the ends of that thing. And that should give us just the characters that are the word. So let's evaluate this and see if it makes more sense. Ah, there we go. So now we're getting some five letter things. That's looking good. We still have, so I probably want to print out line.strip too. Okay, just so I'm stripping off that new line character. There we go. So you'll notice that some of these are questionably words from the English language. Abaft is a weird one, but I think that's some kind of nautical speak. About, I don't know, some of these are very interesting. Let's scroll down a little bit more. Oh man, there's a lot of 5-letter A words. Okay, we're finally in the B's. Be wet means to make something wet. Okay, so I'm confident that this is now working. I can comment out this print statement and run this again so that we can just see the outcome of our code here. So out of 370,105 words in the English language, again, we're not sure if this list is comprehensive, about 16,000 of them contain 5 letters and only 5 letters. Let's just check another length. Let's check all the 4-letter words. I'm not going to display them because you might know some 4-letter words that I shouldn't be sharing in a video. Here there's 7,186 of those things. Let's go to 6-letter words. Oh, curiously, there's more of those, 29,000. 7-letter words. There should be some point at which once we get above a certain word length, the number of words of that length starts to go down. So it looks like it's not 7. Is it 8? Oh my goodness. I'm really surprised by this. Okay, so it's slowing down. 10. Did it turn around? Yeah, so I think the previous one was 53,000. There are 53,000 9-letter words, and there are only 45,872 5-letter words, so we've kind of turned the corner. Now, there are some interesting takeaways there. There's some, possibly some interesting reasons for that. Is there a reason that languages would kind of prefer words in that, 8, 9, 10 character sweet spot? Probably because they can convey more information. You can have maybe compound words that have a bunch of different word roots kind of jammed together. Another interesting reason is maybe that if you're thinking about 3-letter words, there are only so many combinations of 3 letters that you can actually make. And then of those, only some of them are going to be actual pronounceable words that have a consonant at least and a vowel at least. So there are just more options when we get to larger words. Let's check to see if there are any 20-letter long words in this data set. Oh my gosh, there are 359 of them. Should we print them out? Let's just take a little. Oh, this looks like a bunch of biochemistry stuff. Anthropobiological. Okay, that seems reasonable. Here's one that's not too weird. Neurophysiologically. Okay, neuropharmacological. Interesting. Let's go down. Super responsibleness. That's what I try to project every minute of every day, is super responsibleness. So you can see that we can take this very kind of straightforward. I mean, this is code that we probably could have written a few days ago. There's not really anything super sophisticated going on here, but we're applying it to a new type of data set, namely text as these isolated words. You can see how we would answer some or solve some of these other problems. We could make a histogram of word lengths. We're not going to do that, but that wouldn't be too many steps more than this block of code that we have above. Now, this data file is kind of fun. You could do a whole bunch of stuff with it. You could ask a whole bunch of questions, like maybe your first name begins with a Z and you're curious how prevalent words that begin with Z are in the English language. You could answer some really sophisticated questions, linguistic questions, such as like, well, English is technically a Germanic language, and in Germanic we don't get too many words that begin with, I don't know, I'm just going to guess, CH. So let's see how many words in the English language begin with CH. Maybe those come more from the Romance languages. I don't know. There's a whole bunch of stuff you could do with this data set. One of the things that you could not do with this data set is investigate how these words are used in context. So because of the nature of this data set, it's just an alphabetical list of individual words. We don't really get any sense of what those words mean or how they're used. I mean, you, because you speak English, could read an individual word. You could read the word super responsibleness and guess that it means like the property of being very, very responsible or something like that. Maybe it means something else, I don't know. But, you know, for a word that we've never seen before and we can't sort out any of the roots of, you couldn't necessarily glean any information from that data set. In order to do that, in order to find out how or investigate how these words are used in the context of human language, we need to investigate a data set that is just that. It's natural human language. So the data set that we're going to move on to here is a very famous data set. It is in fact the novel Pride and Prejudice by Jane Austen, which was written in 1813. Very famous 19th century novel. The language in this novel is wonderful and beautiful, if you're into that kind of thing. This novel contains many of the words that are also contained in words alpha.txt. However, it contains those words in the context of how they are used in language, you know, within sentences. They're next to other words. The relationship between the words and their next door neighbors is very important because they convey actual ideas. So there's a lot going on with this data set. Let me just show you this thing real quick. So I'll double click on this in the Jupyter browser. This is a plain text version of Pride and Prejudice. There's a lot of interesting stuff going on here with copyright. So I got this from what's called Project Gutenberg, which is an ebook service. You can check it out. There's a website link to it somewhere in this document, I think. There's a bunch of formatting stuff in this file. So this paragraph tells you about Project Gutenberg. It's not part of Pride and Prejudice. All of this stuff right here is not part of Pride and Prejudice. It's really only, I mean, table of contents. I don't know if you consider that part of the book. This isn't really language used in its natural habitat as part of sentences. It's only when we scroll down here to really chapter 1 where the book begins. Now, if I'm going to process this data file, process this data file and consider only the language that is part of natural language, I need to have some way to tell my code, okay, read in a whole bunch of lines but ignore them, and then start considering this thing as a book, as natural language at this point. The code I write, the little code cell that we're going to work with in a minute, is going to use this string right here, start of the Project Gutenberg ebook Pride and Prejudice. We will call this, or the line after this line, the beginning of Pride and Prejudice. So we'll read in some lines of data and ignore them until we get to here. Anything we read after there, we're going to consider to be Pride and Prejudice. Similarly, at the end of the book, let me scroll all the way down here to the end. Goodness gracious. Okay. There's something similar at the end of this book, at the end of this ebook. Let's see if we can find it. That tells us when the text of Pride and Prejudice is over. Oh my gosh, there's a whole bunch of fair use and copyright information down here. Okay, there it is. So check this out. End of the Project Gutenberg ebook Pride and Prejudice. So we're going to write some code, or we're going to use the code that I've written in the next tab over, which uses these two lines, beginning of, or start of, whatever it said, I forget, and end of as the two kind of flags that tell us when to begin considering text and when to stop considering text. And you'll see that represented in the code cell we're going to work with here. All right, so here's our code cell. Again, nothing new from a programming standpoint. We're opening up a file, we're reading lines off of the file, and then we're just gonna ask some questions about them. So I open the file, I read the first line. I have a while loop that's basically going to read more lines off of the file, until we get to the line in the file that has start. So it's going to read that line, that while loop will exit, and then it'll get down here to this line, or this while loop. This is where the actual computation happens. So this next loop is going to read until, the way this is coded up is kind of weird, but it's going to keep reading lines off of the file until it finds asterisk, 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 space, end is in the line that it reads off. And I think actually I want to include one more. Line equals file.readLine here, just because we don't want to consider the start line to be the part of the text. All right, let's see what we have here. So this is, I guess we just want to consider this kind of a little shell of code that we're going to use. Yeah, that's what's going on here. We're actually going to move down to this warm-up problem. So let's check this out. This block of code, we're going to copy it and paste it a couple times, maybe just one time. We'll see how many warm-up problems I want to do. But what are the types of questions we could ask? Well, here's a warm-up problem 5. The main character of Pride and Prejudice is Elizabeth Bennet. We're going to count how many times Elizabeth and Bennet appear in the text. Don't forget to consider things like Elizabeth's. Okay. All right, so let's copy this code right here, because this is the kind of core code that's going to parse through this entire data file. Okay, then what do I want to do? I want to count up the occurrences of Elizabeth and Bennet. So let's create some counter variables. Beth's and Bennett's, and we'll start those both at zeros. Looks like that. And then we'll probably want some conditionals down here. We'll do that in 1 minute. And then I'm just going to print out those things. So print out, how do I want to do this? N Elizabeth's, like thus. Okay, let me copy this stuff. There we go, that should work. Probably won't work. We'll see why it doesn't work in 1 minute. And then we'll have Bennett's and Bennett's right here. All right, Bennet. I hope I spelled that correctly. We'll find out in a minute. I'm going to come back up here and correct that spelling. Okay, super. So all I have to do is add some conditionals here. So if Elizabeth is in line, what we're going to do is increment N Elizabeth's plus equals 1. Now, this is incorrect right now. It's not going to do exactly what we want, and I'll tell you why in a minute. But let's just run this and see if the kind of core functionality is working here. So again, what this code is going to do is it's going to read off the junk lines at the beginning of the file and ignore them. Once it reaches this start line, it's going to then read off successive lines in the file. It's going to check whether Elizabeth, the string Elizabeth, is in the line that it read off. This will work, I'm pretty sure. At least it'll run, yeah. And if that's the case, it's going to increment this counter. It's going to keep reading until it gets to this end stuff, the end line, and then it's just going to close the file and print out the values of our 2 counter variables here. Let's see if this works. All right, there we go. So the number of lines that contain the word Elizabeth somewhere in them is equal to 632. Maybe we should, let's do the same thing for, actually, let's leave it. Let me tell you why this is probably not what we want. So can you picture a situation, can you picture a line in the text where this code that I've written, won't do exactly what we want it to do? You can either pause the video or I'll give you 3 seconds to think about it. All right, imagine a line in the file, in the book, in the file, that contains 2 occurrences of the name Elizabeth. So that line, what would happen is maybe there are 2 different sentences here, or maybe it's a sentence like Elizabeth said, "My name is Elizabeth." So that could be a line in the file. I don't know if that's actually in Pride and Prejudice. Those 2 occurrences of the word Elizabeth would only be counted once, because if Elizabeth is in the line, yep, that's doubly true, but this if is only going to be evaluated to true once. So probably what we want to do is we want to check every single word in the data file to see if it contains Elizabeth. That will take into consideration things like Elizabeths, like this, or some other phrasings. So what I'm going to do is I'm going to split this into line list, or let me split it into something called words is equal to line dot, let me strip it first, and then I'll split it. And I'm going to split it everywhere where there is a blank space. Just a space. That's how we separate words in the English language. Okay, and then what we'll do is we will loop over all of the words in that word list. For W in words, okay, I'm going to check to see if Elizabeth is in W. If so, I'm going to increment the Elizabeth counter. And then I'm also going to check do the same type of thing for Bennett. B-E-N-N-E-T-T. I really hope I spelled that correctly, but we'll find out in 1 minute. B-E-N-N-E-T-T. All right. So again, what's going to happen here is we're going to read the line from the file. We're going to split it into a list everywhere where there's a space. That should just give us the list of the words in the line. Then for each word in the line, we're going to check whether Elizabeth is in that word, we're going to check whether Bennett is in that word, and we're going to increment our counter variables appropriately. Let's see if this doesn't crash. All right. So we have, my fear was not confirmed. I think we had 634 Elizabeths before. My other fear was confirmed. I think I misspelled Bennett. I think maybe there's only 1 T in this thing. Let's try that. So maybe she spells her last name with only 1 T. Now this is an example of the code is running. It's not throwing a runtime error. It's just not doing what I thought it would do because I didn't understand my data well enough. So this is a good example of how to do a debug process. Okay, there we go. So the number of Elizabeths, 634, and number of Bennetts, 333. So, we should assume that there are some other characters in the novel that have the last name Bennett too. They're probably referred to by their full name sometimes, or Miss Bennett, some other characters. We should assume that this 333 is a little bit higher than what we actually want. So it's probably an overcounting because some of these Bennett references are not Elizabeth Bennetts. We can probably assume that there aren't too many other Elizabeths in the book, although I admit I don't know that. I don't know if there are no other Elizabeth characters. Anyway, you can see the ratio here. Elizabeth Bennett is probably referred to by her first name twice as often as she is by her second name, by her family name. So let's see what we can do with that. Here's warm-up 6. Warm-up 6 says, Elizabeth Bennett's romantic interest in Pride and Prejudice is Mr. Fitzwilliam Darcy. Let's investigate how Austen, or British people in Austen's time, used first names. Find the number of appearances of Elizabeth, Bennett, Fitzwilliam, and Darcy in the text. Calculate the ratio of first name to last name appearances for each character. So is there a difference in the number of times, or the rate at which each of these characters is referred to by their first name? I'll pause for a moment. Let's see what you think. Which of these characters do you think would be more often referred to by just their first name? Now, there's some challenges there. It's not really apples to apples. Elizabeth Bennet is the main character in the story, but let's just ask the question with data here. So I'm going to copy this entire code cell because all we're going to do is we're going to add some stuff to this for Mr. Fitzwilliam Darcy. There you go. And I'm already counting up the number of Elizabeths. Let me print out here Elizabeth ratio. And rather than reporting each of these things individually, I'm just going to divide the number of Elizabeths by the number of Bennetts and print that out. I'm going to create two more counter variables. I'm going to call one Fitz's. I'm not going to type out all of Fitzwilliam. And number of Darcy's. Okay, looking good. And then I'm just going to do the same thing that I did with Elizabeth's and Bennett's with Fitzwilliams and Darcy's. FITZ William and Darcy. All right, that's looking good. Oops, that's not looking good. I have to increment these. I have to increment the correct variables. Fitz's, yep, that's what I called that. And in Darcy's, okay, cool. And then we will copy this thing and we'll repurpose it for Mr. Fitzwilliam Darcy. Fitz ratio. And Fitz's. In Darcy's. Cool. Any other problems? Can you see any other potential problems? So none of the file reading machinery has changed here. I'm basically just keeping track of more occurrences, more variables. That looks good. We could probably simplify this a little bit by making these last three ifs, else ifs. Chances are good that if Elizabeth appears in the word, a single word, Bennett doesn't also appear in the word, Fitzwilliam doesn't also appear in the word because these things are different words, but we'll leave it as is. The code could be more efficient, but I'm not real worried about that right now. Okay, so check this out. The ratio for Elizabeth Bennet, her first name is used almost twice as much as her last name. Okay. Fitzwilliam Darcy, his first name is used, what is this? 8.6% of the number of times his last name is used. That's pretty wild. Now, again, there could be other characters in the novel with the last name Darcy. Maybe there are a lot of them. I don't think there are 20 more characters with the last name Darcy, which would make these ratios probably more equal, but there's a big discrepancy there. So this is interesting. Maybe speaks to gender roles in 19th century England. It maybe speaks to the type of novel this is or how the character's narrative is portrayed. This is the beginning of applying quantitative analysis to possibly asking some questions about the human condition and how it's presented in this novel, which is kind of cool. All right, well, I think it's kind of cool. You might not think it's kind of cool. But hopefully you can see how the basic tools we've developed in previous lessons, we're applying them to a completely different type of use case here, a completely different realm of investigation. Okay, so these calculations might seem kind of trivial. We're not going to find the cure for cancer in an 1813 novel, Pride and Prejudice. I tend to agree with that sentiment, if that's a sentiment you have. However, this idea of treating text as data is not that far removed from the physical sciences, or at least the biological sciences. For example, here's some text, GCTCGGGTGA. I could read all of those, I'm not going to. You might know that this could look like the representation of a double helix of DNA, where you have these base pairs, these pairs of, what are these things called? Whatever they're called. What are those things called? Put in the comments what these things are called. Analyzing DNA strands like this, genetic code, could lead to a cure for cancer. And a lot of the skills that we've used above could be adapted to text like this very easily. All right, so here's one more example. Let's talk about cryptography and cryptanalysis. So cryptography is the science of hiding writing. So encoding writing so that it is not readable by someone that you don't want it to read, that you don't want to read it. Cryptanalysis is the science of decoding that secret writing, that encoded writing. And it's a fascinating field of study. It's been in existence for thousands of years. It has won and lost wars. Countries have won and lost wars based on the strength of their cryptography and cryptanalysis. The story of the breaking of German codes in World War II is absolutely fascinating. I would encourage you to look into it. It'll blow your mind. Really cool stuff. Also has a lot to do with the birth of computer science. I'm not going to go down the rabbit hole and talking about that more, but I'll give you an idea of how we might use some of these data science skills for decoding an encoded message. So here I have what I'll refer to as some ciphertext. All that means is that this is encoded text. You probably can't read it. Human squishy eyeballs are not very good at looking at encoded text like this and telling what it is, decoding it. But there are some first steps that we could make in trying to decode this message that draw from our data science toolbox. I'm just going to show you an example of that now. So what we're going to do first is we're going to make a bar graph of the frequency of letters in Pride and Prejudice. And this seems like has nothing to do with this encrypted message. You'll see where I'm going with this in 1 minute. So what we want to do is we want to count up all of the letters in Pride and Prejudice, and we want to just make a bar graph of the frequency of those letters. All right, so what I'm going to do is I'm actually going to go up here to the top of this notebook, and I'm going to grab this little thing. Where did I put it? Alphabet. I probably could have retyped that, and actually I am going to, I'm not going to retype it, so I'm just going to copy that thing and paste it down here. And the first thing that I'm going to do, if you think back to our data visualization lesson, in order to make a bar graph, I probably want a dictionary. So I have this thing, alphabet. What I'm going to do is for letter in alphabet dot split, and I'm just going to split the string up everywhere where there's a nothing. So what that's going to do is it's going to take this string and just split it up into a bunch of individual characters. And I can show you that. What I'll do is I'll print out letter. Let's make sure that this works. Empty separator? What? I guess that doesn't work. Well, that's dumb. Okay, so let's do this a different way. So I apologize if that was going to work. Let's do this. For I in range the length of alphabet. Okay, this is totally going to work. And then I'm going to print out the character that's at the ith element alphabet of alphabet, like this. Let's see if this works. If this doesn't work, I'm pausing the video and taking a nap. Hey, there we go. Okay, great. So we took a string with the letters of the alphabet and we turned it into a bunch of individual letters of the alphabet, and we can print these things out. The utility of doing this is I'm going to create a new object that I'm going to call letterdict, which is I'll call it letter dictionary, which is just a dictionary. You may recall that a dictionary is like a list, but instead of integer indices, it has keywords. What I'm going to do is I'm going to basically make a new entry in my letter dictionary that is equal to, so the key is going to be alphabet, the ith element of alphabet, and I'm going to set the value equal to 0. After I've done that, I'm going to print out my letter dictionary. I'm ruining my decision to call this thing letter dictionary because that's a lot to type, but we got what we got. All right, so let's look at this. Boom, there's our dictionary. Okay, so all of this so far is set up. I've created this container, a dictionary container, that's going to store the numbers of each of these letters. Now all I have to do is I have to step through the entirety of Pride and Prejudice and check every letter, and if each letter in Pride and Prejudice is equal to one of these, I increment the value corresponding to that letter in my dictionary. So there's a little bit of funny business that I'll have to do, but we'll fix it in a minute. Okay, so let's go up here. Let's grab all of this code. It worked above. It's going to work below if we change it a little bit. All right, okay. So I do need this stuff which opens the file. I don't need these counter variables. I do need this first while loop because it's going to get rid of the junk text. I do need this second while loop because it's going to consider the text that we actually want. But So this line of code split the line that I read in into just the words that compose it. I don't want to do that anymore. What I want to do is I want to iterate over the characters that are in that line. So I'll use something very similar to what we had above. So I'll say for j in range, which is the length of the line. The letter that I'm going to check is letter is equal to, let's do it like this, line, the jth element of that line thing. And then the first thing I'll do is I have to build in, because there's a lot of characters that are in this data file, like numbers, punctuation, maybe some capital letters. Maybe we can figure out how to deal with capital letters in a minute, that don't appear as keys in our dictionary. And frankly, we just want to ignore them. So what I'm going to do is I'm first going to check if letter is in our letter dictionary dot keys. Okay. If that's the case, what we're going to do is we're going to say letter dictionary. The element that I want to grab is the one associated with letter. So I'm checking each letter, each character that's in this line. If that letter appears in the keys in our dictionary, then I can do this. I can just say, hey, go to the element of our dictionary associated with that letter and increment the value by 1. So it would start at 0. Let's say I find a lowercase e. It's going to go into our dictionary and increment the value associated with letter E by 1. And then that's going to happen over and over and over again. We're going to close the file, and then we will print out our letter dictionary like that. Okay, I said a moment ago that we've coded this up so that we're not trying to access elements of our dictionary that don't exist. So like we don't have, if there's a number 2 somewhere in Pride and Prejudice, we don't want to consider number 2 because it's not a letter. If there's a capital letter in Pride and Prejudice, it's also going to ignore that. We will address that in a moment, or maybe we won't. We'll see how I'm feeling. All right, let's run this. Okay, we got a runtime error. So this if letter is in letter dictionary.keys, it says argument type of built-in function or method is not iterable. I wonder if I just need some parens there. So let's get to the bottom of this. This is an error, runtime error. I thought that the syntax worked this way, and it doesn't. Hey, okay, I just needed some parentheses. Apologies. So letter dictionary.keys returns a list that's just the keys of this dictionary. Now, I've taken the entirety of Pride and Prejudice. I've reduced it down to counts of the letter frequencies. And that's great. I've collapsed an entire 19th century novel, which they are known to be quite long. I've collapsed it into a 26-element dictionary. Glancing at this, I can't really get an understanding of what's going on here. What I want to do is I want to make a data visualization. So let's just, let's do this. I'll add a new code cell down here and we'll visualize this as a bar graph. So we have to first import matplotlib.pyplot, and I'll do that as plt, is just shorthand. I'm going to do plt.bar. And the thing that I want to make a bar graph of is the information in the letter dictionary, like that. And I'll do plot.show. This is just the most basic graph I could possibly make. Most basic bar graph I could possibly make. Let's see if this works. Missing one. Oh, that's right. I need to supply the keys as the first argument and the values as the second argument. I think that's how that works. Hey, there we go. All right, so what is the most frequent letter in Pride and Prejudice? And we'll use Pride and Prejudice as like a proxy for the entirety of the English language. Well, it's our old pal E. You can see this bar graph says that E, or indicates that E appears in Pride and Prejudice almost 70,000 times. The next most frequent letter is T right here. Next most frequent is A. Then after that, it's probably O. The vowels are very popular. You gotta have vowels. Then we have N, then what is this? I, another vowel, H, and then SR, things like that. Okay, so how could we actually use this? Well, I think what we want to do is actually I won't go into too much detail. What I will tell you is that so we're using Pride and Prejudice as a stand-in or an example of a large corpus, a large data set of normal English language in context text. And we're seeing the frequencies of each of the letters in that text. What we're now going to do is we're going to take this ciphertext and we're going to do the same type of thing. So if we believe that this ciphertext is just a simple letter substitution, meaning something like, okay, everywhere where you see an M, that M actually stands for an L. Everywhere where you see a W, that W actually stands for an O, and so on and so forth. What we're going to do is we're going to make the same type of bar graph for our ciphertext. And we're going to compare those two bar graphs. What it will allow us to do is compare the letter frequencies. So if we make a bar graph for the ciphertext and we find that the occurrence of capital J's in our ciphertext is way, way higher than all of the other letters, that's a good reason to believe that capital J represents E in our ciphertext. So we're taking the letter frequency bar graphs and basically just comparing them as a first pass toward decrypting our ciphertext. Okay, so how do we do that? Well, some nice person has made a code cell that has the ciphertext already in it. All we need to do is the same stuff to make a dictionary that we did above for Pride and Prejudice. So I'm going to go up here. I'm going to copy the entirety of this cell. Okay, we're going to throw away most of it. Okay, there it is. So we do want to create, okay, I'm going to rename letter dictionary to cipher dictionary, just because we want to have two separate dictionaries for the two text bodies. And okay, we're going to create a new dictionary. Now I can get rid of everything that has to do with Pride and Prejudice. I don't have to read in a bunch of junk lines. I don't even have to read in any lines. What I do have to do is I have to iterate over the, did I indent that correctly? What I do have to do is I have to iterate over the characters in this ciphertext string that's above that I'm calling ciph. Okay, so what we want to do is we're going to want to go for j in range, the length of ciph. So we'll iterate over all of those things. Letter is going to be equal to the jth element of ciph. If letter is in cipher dictionary, dictionary.keys, then cipher dictionary, we're going to increment the corresponding values. Cipher dictionary letter plus equals 1. I don't have to close the file. There is no file to close. I'm going to print out cipher dictionary. And then you know what? Gosh darn it. I'm just going to steal the lines of plotting code from above here and just do it all in one cell. All right, we're looking good. Instead of making a bar graph of letter dictionary, I'm going to make a bar graph of cipher dictionary. Same type of thing here. Dictionary, and I think this might work. All right, are we ready? It didn't work at all. Any guesses why it didn't work? So we still get a dictionary that's looking good. Any guesses why this didn't work? So let's check to see. So we're iterating over all of the characters in the cipher. We're checking to see whether the letter that we get in the cipher, the jth element of the cipher string, is in the set of keys that kind of, oh goodness, the set of keys that define our dictionary. And if so, then we increment. Ah, I see what the problem is. Actually, I saw the problem the whole time. I saw the problem as soon as I made it. I figured it would be a teachable moment. Our ciphertext is a very dumb problem. Our ciphertext is all capital letters. Our dictionary keys are all lowercase letters. There are a couple different ways that we can fix this. We're going to use the dumbest possible way. And what I mean by that is I'm just going to retype this entire alphabet in caps. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. I think I got all of them. Okay, I did get all of them. I'm going to turn off caps lock just so I don't make any blunders later on. Now, this is not going to be a problem because all we're doing is comparing the frequency of these symbols. At this point, the ciphertext, they're really just symbols. These could be emoji as far as we're concerned. We're going to try and decrypt this thing by considering the letter frequencies. All right, so here's the letter frequency for our ciphertext. It looks like L is the most common letter. Not by a huge margin, but by, I don't know, 10% margin, something like that, by 3 out of 30-ish, something like that. K is the next most common letter, and Z is the next most common letter. So my first pass at cryptanalysis, cracking this code, would be to say, okay, let me try out replacing L, the most common letter in my ciphertext, with E, the most common letter in the English language. Let's try that as a first pass. Let me try replacing K in my ciphertext, the second most frequent letter, with T in the English language, the second most frequent letter in the English language. And finally, let me try replacing, where is it? Let me try replacing Z in the ciphertext with A, the third most frequent letter in the English language. That's a really good first pass for a simple code like this. This is a very simple cryptographic scheme, encryption scheme. And from there, we can't really rely on a one-to-one correspondence between the frequencies of letters in general English text and the frequency of letters in our encrypted message. There are a couple reasons for that. One is that our encrypted message is very short compared to Pride and Prejudice. It could be that, there just weren't enough words to include a word that contains J or K or Q or something like that. Actual J or K or Q, not the encrypted symbol. But that's a good first pass. That's better than just guessing at the letter correspondences or the letter equivalents in our encrypted text. So this is very cool technology. It's not new technology. So again, in World War II, computers were developed largely to do this type of analysis on encrypted messages. Very, very cool history. I'm not going to go into detail. I'm reining it in here. Very cool stuff. You can read up more on it on your own time. So I've got a couple homework problems here. I will add to these homework problems. If you can completely decrypt this ciphertext, that would be a fun thing to do. So it's not 100% a science. There's going to be some art to it, but there still is a logical process to step through to test. There'll be a little bit of guess and check method. All right, we'll leave it there. Thanks for your attention. Hope to see you online and in the comments. Have a great day.